Hello, my name is Phoenicia. I would like to introduce to you our work, LoopDA, constructing self-loops to adapt nighttime semantic segmentation. Dealing with adverse driving conditions such as nighttime is challenging for the deep learning-based perception system of autonomous vehicles. Models that are trained on sunny daytime datasets fail to perform equally well when applied directly to images captured at nighttime. Considering the lack of training labels and the difficulty of annotating, performing unsupervised domain adaptation from the labeled daytime source domain to an unlabeled nighttime target domain has been widely researched to enhance model adaptability. In addition to the labeled daytime dataset, existing nighttime datasets usually provide nighttime images together with corresponding daytime reference images captured at nearby locations for reference. The key challenge is to minimize the performance gap between the two domains and how to take full advantage of the unlabeled daytime reference data owing to their much smaller domain gap. In this paper, we propose LoopDA for adapting nighttime semantic segmentation. It assumes that there is an intrinsic looped connection between the input image and its segmentation output. In other words, if a pixel region in the RGB input is correctly assigned to a certain semantic class, this class distribution should in some way correspond to a specific pattern back in the input space, which leads to such semantic prediction. Therefore, the predicted semantic maps should get rectified if they take part in correctly recovering the exact input data in a self-loop. Furthermore, to reduce the impact of pose shifts and make good use of the daytime reference data, we propose a DNA technique in a co-teaching pipeline, bringing substantial benefits to enhance nighttime segmentation. To be specific, during training, the segmentation network takes all data and outputs the encoded features and the predicted semantic maps. Note that, to condition our network, the daytime source domain is trained under full supervision. For refining the model, self-inner loops are first constructed with help of either a daytime or nighttime image decoder that contains our proposed semantic rendering layers. These self-loops result in recovering the input data using the predicted semantic maps by rendering them into the encoded features. In a similar fashion, we also construct outer loops which include intermediate cross-domain data generation steps to enable bidirectional model optimization between day and night. With the constructed inner and outer self-loops, the domain gap is gradually minimized via intradomain refinement and interdomain alignment. And the predicted semantic maps for the target domain get rectified accordingly. In addition, we also perform self-training on the unlabeled data using the pseudo-labels. For pseudo-labeling at nighttime, we propose a co-teaching pipeline that involves an offline pseudo-supervision signal from the trained warm-up phase and an online reference-guided signal based on our proposed DNA technique. For the reference-guided pseudo-label selection, DNA indicates the day-night agreement in the predicted labels that contain static objects. DNA tackles the pose shifts efficiently and helps to produce high-quality pseudo-labels for the nighttime target domain data. Both qualitatively and quantitatively, LoopDA outperforms prior arts when evaluated on the popular Cityscapes to Dark Zurich adaptation benchmark. For details about training LoopDA and more ablative analysis as well as its potential extension to other tasks, please refer to our paper. Thanks for your attention.